What if I told you that in less than a year, we're about to lose our only chance to study the most mysterious visitor our solar system has ever seen? On October 29, 2025, something unprecedented will happen that has astronomers around the world holding their breath in anticipation and dread. 3IAtlas, only the third interstellar object ever discovered, will vanish behind our sun's blinding glare, taking with it secrets from another star system that we may never get the chance to unlock again. But here's what makes this cosmic disappearing act so much more significant than you might think, and why some scientists are calling it the astronomical heartbreak of the century. This blackout period isn't a matter of days. It will last nearly 6 weeks. During that time, the most massive interstellar object ever detected will be moving unseen through space, its path completely hidden. And the timing couldn't be worse. That same window covers Atlas's perihelion, the moment it comes closest to the Sun. In comet science, perihelion is when things get exciting. Icy nuclei flare up, jets ignite, tails form, and crucially, orbits can shift. Yet during this defining moment, Earth will be blind. The geometry is merciless. The Earth, the Sun, and 3IAtlas line up almost perfectly, placing our planet on the wrong side of the solar furnace. No ground-based observatory will be able to separate Atlas's faint glow from the blinding light of the Sun. Even powerful space telescopes like Hubble and the James Webb Space Telescope will be forced to shut their eyes. Their safety systems simply won't allow them to risk pointing so close to the solar disk. What's left is only a thin lifeline, a few solar probes and coronagraphs. These instruments were built to study solar storms and coronal mass ejections, not faint interstellar visitors. Their sensitivity is poor for something as dim as Atlas, meaning at best they might capture a few vague traces. For most astronomers, the blackout represents a total loss of visibility at the very moment the object's secrets might be revealed. This enforced silence means we won't know whether Atlas behaves like an ordinary comet, or whether something far stranger is happening. If there's any change in speed, any unexpected burst of activity, or even a maneuver that alters its trajectory, it will all happen where no one on Earth can watch. And when Atlas finally re-emerges in December, we may discover that the story has already changed in ways we never saw coming. Before we dive in, hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like so we know to keep uncovering them. Harvard astrophysicist Avi Loeb has never been shy about questioning the mainstream, and with 3IAtlas, his claim is as bold as it is unsettling. Loeb suggests that this massive interstellar body could do more than simply pass through our solar system. At perihelion, hidden behind the Sun, Atlas might execute a maneuver, whether natural or engineered, that would slow it down just enough to stay. In other words, instead of racing back into interstellar space, Atlas could become a permanent resident of our cosmic neighborhood. The idea sounds extraordinary. By default, interstellar objects are just visitors, moving on open-ended, hyperbolic trajectories that carry them in and out of the solar system forever. Both Oumuamua in 2017 and Borisov in 2019 followed that exact pattern. Quick entries, quick exits, never to return. But Loeb points out that Atlas is different. Its sheer size, its strange chemistry, and its puzzling dynamics all open the door to an alternative scenario. Here's the critical point. At its closest approach, Atlas will be moving at nearly 44 kilometers per second. That's an interstellar bullet. But if its velocity changes by just a few kilometers per second at the right moment, it could swing into a bound orbit around the Sun. A tiny adjustment compared to its overall speed, yet the consequences would be enormous. For the first time in history, humanity could be looking at an interstellar object that stays within reach, circling our solar system like a captured alien moon. The timing of this supposed maneuver makes it all the more mysterious. Because it would happen during the blackout window, Earth-based telescopes will see nothing. If Atlas does alter its trajectory, no one will witness it live. Instead, the evidence would only appear later, written into its orbit when the comet re-emerges from behind the Sun. Loeb frames the case not as proof, but as a possibility worth preparing for. To him, when you see enough anomalies clustered together, mass, trajectory, chemistry, it becomes irresponsible to dismiss them outright. If Atlas does remain, it would overturn everything astronomers expect from interstellar wanderers and force us to rethink the boundaries between natural phenomena and something else entirely. From the moment astronomers first measured 3IAtlas, one number dominated the conversation: 20 kilometers. That's the estimated diameter of its nucleus, a staggering figure compared to every interstellar object seen before. For context, Oumuamua, the first interstellar visitor detected in 2017, was less than a quarter of a kilometer long, basically a cosmic shard. The second, Comet Borisov in 2019, stretched perhaps a single kilometer wide. Both were small, faint, fleeting. Atlas, by contrast, is a giant, easily an order of magnitude larger than what surveys expected to find first. Its size isn't just speculation. Astronomers derived it from brightness measurements corrected for distance, solar angle, and known reflectivity of cometary surfaces. The conclusion was hard to escape. Only a massive solid body could shine with that magnitude without the kind of dense coma that usually inflates a comet's apparent size. That same brightness translates into a mass estimate of over 33 billion tons, enough material to build multiple mountains. By any measure, Atlas is in a league of its own. This scale raises serious questions. According to statistical models, the sky should be filled with countless smaller interstellar wanderers, tiny rocks and icy fragments outnumbering giants by orders of magnitude. Surveys like Pan-STARRS, Atlas, and soon the Vera Rubin Observatory are tuned to find these faint objects, scanning the heavens night after night. Yet the first two interstellar bodies detected were indeed small, right at the edge of visibility. And then suddenly, a massive 20-kilometer behemoth appears out of nowhere. For many scientists, this doesn't add up. If the discovery pipeline is working, then giants like Atlas should be discovered only after hundreds, maybe thousands, of smaller cousins have already been cataloged. Instead, the record jumps straight to an outlier. To Avi Loeb and others who pay close attention to anomalies, this leap is more than surprising. It's suspicious. A body this large, arriving so soon in the sequence of interstellar discoveries, stretches probability beyond comfort. Whether Atlas is a statistical fluke, the tip of a hidden population, or something entirely unexpected, one thing is clear: its sheer size and mass make it the most significant interstellar object ever observed. And if it does stay in our solar system, we won't just have a visitor. We'll have a permanent heavyweight neighbor unlike anything seen before. Comets are alive with motion. As they approach the Sun, heat boils their ices into jets of gas and dust, producing not just glowing tails but tiny rocket-like thrusts that push them off course. Astronomers can measure these deviations precisely. Even Oumuamua, small, dry, and strange, showed a faint but undeniable acceleration that gravity alone couldn't explain. It was a key piece of evidence that sparked years of debate. But Atlas refuses to play by those rules. Despite violent activity, it shows no detectable non-gravitational acceleration at all. This is astonishing because Atlas is not a quiet body. Observations indicate carbon dioxide is blasting off at rates of 100 to 150 kilograms per second, the kind of mass loss that should absolutely nudge it in measurable ways. A jet stream of that magnitude is like dozens of fire hoses spraying into space non-stop. Normally, even a fraction of that activity creates noticeable shifts in trajectory. Yet with Atlas, the orbit remains perfectly gravitational, tracking the Sun as if no outgassing exists. This paradox leads to two equally dramatic possibilities. The first is that Atlas is unimaginably massive and dense, so large that the gas jets barely move it. This would push the size and weight estimates even higher than current models suggest, reinforcing the idea of a mountain-sized interstellar giant. The second possibility is stranger, that something about Atlas isn't natural at all. Avi Loeb and others have floated the notion that the lack of push could mean the jets are somehow directed, controlled, or artificial in nature. If Atlas were hollow, metallic, or even engineered to maintain a stable orbit despite active venting, the absence of acceleration might make sense. For mainstream astronomers, a less exotic explanation may lie in geometry. Perhaps Atlas's jets are so evenly distributed across its surface that the forces cancel out, leaving the body's motion unchanged. But even this tidy answer feels unsatisfying given how chaotic most comets behave. One way or another, the acceleration paradox is a red flag. Either Atlas is vastly heavier than we thought, or its activity obeys rules we've never seen before. And during its hidden perihelion, this puzzle could hold the key to understanding whether we're watching a natural visitor or something far more deliberate. Numbers don't lie, or at least, they shouldn't. Population models built by planetary scientists tell us something simple. Small interstellar objects should vastly outnumber large ones. Think of it like cosmic sand. Just as beaches are filled with countless grains and only a few boulders, space should be littered with tiny wanderers. Rocks and ice fragments a few meters to a few hundred meters across. Giant bodies 20 kilometers wide, like Atlas, should be the rarest of the rare. So how is it that our first confirmed interstellar objects follow the exact opposite pattern? First came Oumuamua, small but still much larger than the pebble-sized fragments the models say should dominate. Then Borisov, about a kilometer across, again far bigger than expected for such an early discovery. And now Atlas, dwarfing them both at 20 kilometers wide and billions of tons in mass. This leap in scale is not just unexpected, it's statistically bizarre. According to probability, astronomers should have detected hundreds, even thousands, of smaller interstellar visitors before stumbling onto a giant. Surveys like Pan-STARRS, Atlas, and soon the Vera Rubin Observatory are designed to spot faint, fast-moving objects. If the models were right, the sky should be teeming with small interstellar debris by now. But the data show otherwise. That mismatch raises two possibilities. The first is that our surveys are missing something. Perhaps the smaller visitors are slipping past undetected because they're too dark, too fast, or too unpredictable in brightness. If true, it means our picture of interstellar populations is incomplete, skewed by observational bias. The second possibility is more unsettling. Maybe the models themselves are wrong because these objects aren't part of a natural, random population. Perhaps what we're seeing is a curated sample. Larger, stranger bodies arriving by mechanisms we don't yet understand, or even introduced by design. Either way, Atlas is an outlier stacked on top of other outliers. The odds of finding such a giant so early stretch probability to its breaking point. For scientists, that makes Atlas more than just another comet. It's a statistical alarm bell, ringing loudly across the field of astronomy, demanding answers about how such a massive visitor appeared in our skies at all. Every comet has a story written in its orbit. Most interstellar visitors approach from random directions, cutting steep angles through the solar system before vanishing back into the void. That's exactly what astronomers expected when they traced the path of 3IAtlas, until the details came into focus. Instead of plunging in from some odd angle, Atlas approaches on a track that hugs the ecliptic plane, the thin disk where nearly all the planets orbit the Sun. That alone is rare. Statistically, the odds that an interstellar body just happens to align with the same flat plane occupied by our worlds is extremely low. Yet, Atlas does exactly that, weaving itself neatly into the geometry of our solar system. But the strangeness doesn't stop there. As it passes through, Atlas is set to perform a series of close planetary encounters, first with Mars, then with Venus, and later a distant interaction with Jupiter. To planetary scientists, this sequence is uncanny. Natural interstellar visitors typically don't line up for multiple planetary flybys in a row. But spacecraft do. Engineers design probe trajectories to exploit planetary assists, slingshotting from one world to another in order to save fuel and fine-tune speed. The resemblance is hard to ignore. Atlas's path looks less like a random visitor's and more like the carefully calculated course of an interplanetary mission. Each flyby occurs at just the right time, in just the right order, to maximize gravitational interactions, almost as if the object were navigating rather than drifting. Skeptics point out that probability allows for coincidences, and gravitational mechanics are universal. Given enough interstellar objects, one might eventually trace a path like this by sheer chance. But even they admit the precision here raises eyebrows. Combined with its immense size, strange chemistry, and anomalous behavior, the trajectory begins to look like one more piece in a pattern of unlikely alignments. If Atlas were a probe, this is the exact kind of course it would follow, sweeping close to planets, harvesting momentum, and setting itself up for a long-term orbit around the Sun. Whether coincidence or design, the suspicious trajectory keeps fueling speculation that 3IAtlas is more than just an oversized comet. From the very first images, 3IAtlas refused to look like a normal comet. Instead of sporting the familiar swept-back tail pointing away from the Sun, it displayed a forward-facing glow, a luminous haze that seemed to shine ahead of its motion. This baffled observers. A comet's coma and tail are supposed to be pushed by solar radiation and the solar wind. Seeing light concentrate in the opposite direction hinted that something unusual was at work. Either a geometric illusion, a strange interaction with solar particles, or something even more exotic. As weeks passed, Atlas revealed another surprise: a bright green emission radiating from its coma. At first glance, this looked familiar. Green glows are often caused by diatomic carbon, the so-called swan bands that give comets their eerie emerald shine. But closer inspection complicated the story. Alongside the C2 signature came strong hints of cyanogen, CN, and the balance between the two didn't match ordinary comets. Then came the most dramatic finding of all: the chemistry of its ices. Spectroscopic analysis revealed an astonishing CO2 to H2O ratio of nearly 8:1. On Earth, and in nearly every comet studied, water is the dominant volatile. CO2 plays a secondary role at best. But in Atlas, carbon dioxide overwhelms water by almost an order of magnitude. This is profoundly abnormal, raising questions about where this body formed and what conditions could have produced such chemistry. Some scientists argue Atlas might have originated in a star system with radically different ice formation zones, where CO2 condensed far more readily than H2O. Others suggest it could be a fragment of a larger, exotic body, something more akin to a carbon-rich dwarf planet than a comet. For Avi Loeb and those open to non-natural explanations, the chemistry looks like a signature, even a design choice, rather than random planetary formation. Taken together, the forward-facing glow, the unnatural green emissions, and the alien volatile ratios, Atlas's optical and chemical oddities push it further outside the boundaries of what astronomers expect. Whatever Atlas is, it isn't playing by the rulebook of ordinary comets. Everything comes down to Perihelion, the moment when 3IAtlas makes its closest approach to the Sun. At that instant, the object will be moving at extraordinary speed, racing along at nearly 44 kilometers per second. On a natural trajectory, that velocity is more than enough to sling it back out of the solar system forever, just as every interstellar visitor before it has done. But here lies the astonishing twist. A change of only about 8 kilometers per second, less than a 20% adjustment, could completely alter its fate. That tiny tweak is the difference between a visitor and a permanent resident. With just the right reduction in speed, Atlas would no longer be on a hyperbolic escape path. Instead, it would be caught by the Sun's gravity, looping into a bound orbit and effectively staying in our solar system forever. It would be the first interstellar object not to pass through, but to remain, circling alongside our planets, like a captured intruder. The possibility itself isn't what unsettles astronomers most. It's the timing. This crucial maneuver point happens right behind the Sun, during the 6-week blackout window, when Earth-based and even most space-based telescopes are blinded by solar glare. In other words, if Atlas changes its trajectory at perihelion, humanity will not see it happen. We'll only discover the truth weeks later, when the comet emerges from behind the Sun and its orbit can be recalculated. This setup almost feels scripted. The exact moment when Atlas could prove itself extraordinary is also the exact moment it's hidden from our eyes. Natural coincidence? Or something more deliberate? For Avi Loeb and others who see patterns in Atlas's anomalies, this blackout makes the event all the more suspicious. It means that if a maneuver does occur, natural or otherwise, it will happen completely unobserved, leaving us only the after effects to analyze. The perihelion isn't just a turning point in the comet's path, it's the critical maneuver point that could redefine Atlas from a fleeting traveler into a permanent mystery, orbiting our Sun. When it comes to 3IAtlas, the scientific community is divided. On one side stands NASA and most professional astronomers who insist that Atlas, while unusual, is still within the realm of natural comets. To them, its mass, trajectory, and chemistry may be surprising, but not impossible. Nature, after all, is diverse and often stranger than our models predict. For this camp, Atlas is simply an outlier. One more data point expanding our understanding of how planetary systems form and evolve. Their argument is grounded in caution. Extraordinary claims require extraordinary evidence, and nothing observed so far has crossed that threshold. Forward-facing glows, green emissions, and statistical oddities can all, in principle, be explained by natural processes we don't fully grasp yet. For mainstream science, it's better to refine the models than leap to exotic explanations. But Avi Loeb takes a different stance. For him, anomalies don't vanish just because they're inconvenient. He argues that when so many red flags cluster together, an enormous size, a trajectory that mimics spacecraft flybys, an acceleration paradox, and alien chemistry, it becomes irresponsible to brush them aside. Loeb doesn't claim Atlas is artificial outright, but he insists that the possibility deserves open consideration, rather than being dismissed with a shrug. This tension between mainstream caution and outsider boldness is not new. The same debate played out over Oumuamua, when Loeb suggested it might be an interstellar probe, while most astronomers insisted it was just an oddly shaped rock. Atlas reignites that controversy on a far bigger scale, literally and figuratively. In the end, the divide isn't just about one comet. It's about how science handles the unknown. Do we lean on established models until the evidence breaks them beyond repair? Or do we treat anomalies as signals pointing to something fundamentally new? With Atlas, that philosophical battle is playing out in real time, and the stakes could not be higher. After disappearing behind the Sun, 3IAtlas will finally re-emerge from its 6-week blackout in December 2025. This is when the world's most powerful, Telescopes, from ground-based giants to orbiting observatories, will train their sights on it. Astronomers will scrutinize every aspect of the comet: its orbit, its rotation, its brightness, and its spectral signatures. Any change, however subtle, could rewrite our understanding of this mysterious interstellar visitor. But the story doesn't end in December. By March 2026, Atlas will approach Jupiter, offering a second critical opportunity to observe its motion. The gas giant's immense gravity could reveal whether the comet remains on a hyperbolic escape trajectory or has been nudged into a bound orbit. If its path is altered in ways that can't be explained by normal gravitational interactions or outgassing, it would lend weight to Avi Loeb's extraordinary hypothesis that Atlas might not just be a natural object passing through, but potentially something far more unusual. Until these observation windows open, the comet exists in a state of cosmic suspense. Its disappearance behind the sun created a perfect blind spot, keeping humanity from witnessing any defining maneuvers. Scientists will have to piece together the evidence retroactively, comparing pre- and post-conjunction data to understand what really happened at Perihelion. For researchers, December 2025 and March 2026 are more than just dates on a calendar. They are the moments when theory meets reality. Will Atlas behave as predicted by conventional comet science, or will it defy expectations once again? The answers from these upcoming windows will determine whether the debate remains theoretical or finally enters a decisive phase. For now, all that can be done is to wait, watch, and prepare for one of the most closely monitored interstellar events in human history.